So that's unfortunate. We had some technical delays, but hello and welcome to the very last few lectures of discrete mathematics to DM3. So let's just pick up where we left off last time, right? So we were talking about closures, right? And we said a closure is the just you have a property omega, and you have a relation that doesn't meet this property, and so you add just enough to the relation so the property is met. Okay. Oh no, sorry, and screen brush. So let's use our screen brush tool as always to draw some of these nice little squares and things. All right. Are we all good? Everyone here? All right. Okay. So we have our relation omega, and we have a property omega, and our relation Q, we say is the omega closure of R, to mean you add enough to R so that you get Q, and Q will satisfy omega. Okay. So please continue to ask if you have questions. Okay. So let's look at a simple diagram to see what that will be. Is closure a function? So closure is not a function. Sometimes it is, but it usually isn't. So here is from last time we showed some examples. I've posted them to the abridged lecture notes. So I'll just open that up really quickly and we can look at them there. There's a few examples here from last time, so I'll just pull them real quick. So the reflexive closure, remember, if you have a relation R and it doesn't have loops everywhere, then you just add loops, and that's the reflexive closure. Okay. If it doesn't have arrows going in both directions, it's not bidirectional, then you just add all the missing arrows. Right. So this was from the previous lecture, the lecture before the previous lecture. And then if it doesn't have, if you can't take a path and squeeze it down into a shorter path, so you add the transitive arrows. And if you want the empty paths, you get the reflexive transitive closure. Okay. So this is what we were talking about not too long ago. So good question, Eddie. Good question. Alrighty. Let's look at some diagrams together just to see what we have. So here's a diagram on 6 nodes. Let's look at a smaller one on 4 nodes. Okay, so this diagram on 4 nodes. It's clearly not reflexive. We have to add some arrows to make it reflexive, right? To get the reflexive closure, we have to add some arrows. Okay, so who knows what arrows we should add? Okay, who knows what arrows we should add? Right. So let's practice together. What should we add? What arrows are needed to make this into a to get the reflexive closure of this graph? Right. Let's try to figure it out. So please type into the chat and we'll talk about it. So somebody says we need an arrow to go from 2 to 1. Reflexive, please look here. Please look here. Reflexive means we want the loops. The loops is what we want. Okay. What you're talking about is symmetric. So good try. All right. Exactly. We just add in the self loops. Right. So we add one right here. We already have this one. We add one right here, and we add one right here. Okay, so we added 3 new edges, and that now we have a reflexive graph. Okay, so the closure is add just enough. Okay, so if I added one more, for example, from 2 to 1, this is not the reflexive closure. This is not the reflexive closure because I have an extra arrow here, right? Closure means just the minimum required to make it happen. Okay, so this extra one is extra junk. The closure just says just add enough. We want to add just enough to make the result reflexive. Okay, this one is extra. It doesn't make the result reflexive. It's extra garbage. Okay. So let's try another one. Let's go to a graph on 2 nodes. Okay. How do we make this graph reflexive? 5, 4, 3, 2, 1. Okay. So it already has one right here. It's just missing one more. It's missing one right here. If we add that one in, we're done. It's reflexive. Excellent. Good job. Now, here's going to be an interesting one for you. What if we go down to 1? Okay. How do we make this one reflexive? 5, 4, 3, 2, 1. Enter your guesses now. All right. So we just need to add the minimum number of arrows to make it reflexive. In this case, we just need one self loop. And that's it. Good job. Good job to everyone who's participating. And if you're participating at home and just not talking in chat, good job nonetheless. Okay, ducks. Alrighty then. What about this one right here? This is the graph with zero nodes. How do we make this one reflexive? All right. So you can see it's right here. It's very small. It's the empty or the null graph. There's papers on this. There's at least one paper on this graph. So what do we have to do to make this one reflexive? 5, 4, 3, 2, 1. Exactly. Good job, Mohammed. We do nothing because reflexive means for every node there's a self loop. So let's look. Yeah, I see that. All the 0 nodes right here, all 0 of them have a self loop. So we're already done. Okay. So today we're going to be talking about the opposite of a closure, which is a kernel. A kernel says, let's find the smallest part of the graph that has the relation we're interested in. So it's the opposite. Instead of adding stuff, let's take away just enough to make it work. Let's take away just enough so the property holds. So let's look at a 6-node graph. Okay, so here's a graph. This graph, how do we make this graph reflexive? What can we take away to make this graph reflexive? All right. So if we take away any of these edges, that doesn't change anything. It will continue to be reflexive. There's nothing we can do to make this graph reflexive. Okay, so the reflexive kernel of this graph does not exist. Okay, here's a smaller one. Right. So this one, there's nothing we can do. We can't take anything away to make it reflect, to get a reflexive subgraph. Right. So the kernel is about taking. So we can't take nodes away. We can only take edges away. All right. So sorry about that. To make that clear, we can't take nodes away. We can only take edges away. Okay. So here there's no edges to take away. I cannot make a smaller subgraph that is reflexive. So the only way to take to get the reflexive kernel of a graph is if the graph is already reflexive, right? Because when you're making the kernel, you're taking edges away, and for it to be reflexive, well, you can only take other parts away. You need it to be reflexive as it is. Okay, ducks. So right here, we're saying, how do I make this one? How do I make this one symmetric? Right. Well, I need an arrow to go back. I need an arrow to go back. I need an arrow to go back. So because I don't have the arrows to go back, I'll just throw away these edges. And then what I'm left with, this middle part, is already symmetric, and I'm done. Okay. So I dropped all the parts that made the relation not symmetric. I dropped all of those parts, and I'm left with something that is symmetric. Okay. So just wanted to mention that. We didn't get to talk about it yesterday, so hopefully some fun stuff. So we talked about reachability yesterday, so I won't spend too much time on it. Let's have one problem. Let's have one problem. Okay. Let's have a 7 node. Let's go for 9. Okay. So question. Here's a very funky graph. Is 3 reachable from 1? Does anyone know? 5, 4, 3, 2, 1. Is 3 reachable from 1? All right. Can I start at 1 and get to 3 somehow? Yeah, exactly. There's this one directly. We can go directly from 3 to 1. Not too difficult. Directly, right there. Okay. All right. Let's do something interesting. Can I go from 1 all the way to 5? All right. Can I go from 1 all the way to 5? All right. So is that reachable? Is there a path to get me from 1 to 5? 5, 4, 3, 2, 1. Yes, excellent. I like how fast everyone's going. I can go from 1 to 3 and 1 to 5. All right, excellent. Is there a cycle involving 1? All right. Is there a cycle involving 1? All right. So 5, 4, 3, 2, 1. A lot of people answering yes. I'm really glad you guys are participating. I literally spent all morning writing this code to make these graphs. So I'm glad you guys are participating. All right, so where's the cycle involving 1? 1 can go down to 3. It can go back to 2. All right, it can go back to 2. And then from 2, we can go all the way back to 6. And from 6, we can go all the way back to 1. So there's a cycle. Okay, excellent. All right, finally, is this graph connected? All right, 5, 4, 3, 2, 1. Vote now. That's right. This guy, #sad, forever alone. It used to be 6 in last lecture. Now it's 9. 6 flipped upside down. Cries forever alone in a corner. So not connected. All righty. Let's see what other interesting questions we can ask. Is this a reflexive graph? 3, 2, 1. It is not a reflexive graph because 9 doesn't have an edge going to itself. Okay. Is this all right, that's enough. Let's move on. If you would like to stay, please let me know. But let's move on. All right. So today we're going to talk about topological sort. Okay. So hopefully you're comfortable with connectedness, right? Let's try a smaller one. Just is this graph connected? The empty graph, is it connected? 5, 4, 3, 2, 1. There's a lot of questions. One moment. How do you make the reflexive closure? The reflexive closure means add an extra edge at every node. So the notes on that are here on the abridged lecture notes. So I'll leave that to you. A graph would be considered as symmetric without 9. Aaron, I'm sorry I erased the graph, but I don't think it might have not been symmetric. I think there might have some missing arrows. Not quite sure. Anyhow, so this graph 0, it is connected. So everyone who answered yes, because all 0 nodes are connected to each other. What about this one? 5, 4, 3, 2, 1. Is this a connected graph? I'm glad that helps, Aaron. Please continue to ask questions even when I'm moving on. So the people who answered, it is connected. All the vertices in here that are different from each other are connected. Let's look at 2 different ones. Yeah, I can't see any 2 different ones, so I'm done, right? But if we look at the same ones, there's only one same one, and we're still done, right? So being strongly connected, so E star makes no constraint about them being the same or different. Neither does the converse. This just means there is a path between any 2 nodes, okay? The path could be empty. That's what the star is. And so here we have an empty path, so it's connected. Excellent. All right, let's try 2. This one is this one connected? All right. 3, 2, 1. The answer is no. There's no paths linking 1 and 2. Okay. All right. What about, let's try another interesting one. Let me get a note in here. Generating these randomly, maybe not ideal. Is this one connected? Whenever there's a forever alone one like 3, it's not going to be connected. All right. So let's jump up to 6. That evil 6. So still not connected. All right. Still not connected. All right. So more often than not, it's easy to tell if it's connected or not. You just take a look and be like, is there a forever alone one or not? So last one, is this one connected or not? 5, 4, 3, 2, 1. So this is not connected because of 8. But someone asked a nice, useful question. What's the difference between strongly connected and just being connected? Strongly connected means you can go either way in the path. It doesn't matter. Either way is fine. Okay. So trees always go down. Okay. But trees are connected because you can go up or down. That's what the word connected means. Right. Strongly connected means there's a path going forward or a path going backward. Okay. So sorry, there's a path going forward and a path going backward. I can go from X all the way to Y, and from Y I can go all the way to back to X. There's 2 paths, right? Whereas strongly connected says it doesn't matter. You can zig and zag as long as they're touching. That's enough. There's some touching path. Okay. If your graph is symmetric, then these two are going to be the same. If your graph is symmetric, then the notions coincide. Okay, that's a good question. Good observation, Jay. Alrighty then. So let's go to topological sort. So the book does a very good job of what topological sort is. It's one of these interesting things where the idea is. Let me just write it down. The idea is, here's our theorem. The theorem is if let's use fancy O. If O is a partial order, then it can be extended to a linear order. Okay, so this sounds like an interesting and complicated result about order theory. Okay, so you've seen orders before. Let me show you one right now. Where is a nice little order? Here's an order. So you've seen this order before, right? This order is the way we arrange subsets of the universal set 1, 2, 3. Okay. In particular, notice the set containing 1 and the set containing 2. They're not comparable. They're parallel or orthogonal, if you like. What's bigger, the set containing 1 or the set containing 2? Which one is bigger? Neither is bigger, right? The ordering is not linear. Okay, so linear means you can arrange it in a line, right? So we talked about this back in assignment in midterm 3, I think it was, or midterm 4, when we talked about linearity, right, and comparability, right? So the numbers, the natural numbers can be ordered in a line, but subset inclusion in general is not ordered in a line. Likewise for divisibility, right? Divisibility is not necessarily linear. Okay. Given any two numbers, right? It's not always the case that one will divide the other. Okay. I give you the numbers 2 and 3. Does 2 divide 3? No. Does 3 divide 2? No. So they're not comparable. Likewise, here we have the set containing 1, the set containing 2, and neither contains the other. Right? But we would like to say, hey, it's just a graph. Can I take this graph and just move parts beside each other? So this is what the word topology means. The word topology means to deform or to stretch without tearing, right? So pretend all of these things are made of rubber, right? Then I can move the node here, move that node there, and the lines between them, the edges are made of rubber, so I can move them really far beside each other. Can I make them into a line, right? So that's the question we're asking, right? And last time I said, hey, you might be interested in this, for example, when you have a large project and you want to divide it into smaller tasks. Which task should be performed first, right? If you're taking classes, maybe you should take discrete math 1 before taking discrete math 2. If you're writing a book, some topics in the book should occur before others. And some books, of course, have dependency graphs at the beginning to show you this. Okay, and so we're going to look at a topological sort. And some of you are going to be taking computer science 2GA3, computer architecture, and then you're going to be interested in instruction in scheduling, right? Under the hood, the computer is going to say, under the hood, here's a number of operations. How do I do them? Okay, so here's one thing for you, right? So you have an arithmetic expression, a plus b times a plus b divided by c, right? How do you evaluate this, the order of operations, right? So you can render it as a graph, and then you realize, wait, to perform the multiplication, I need to first perform the addition. To perform the addition, I need to evaluate, get the variable a. And then to continue evaluating the addition, I need to get the variable b, okay? So before I can evaluate the addition, I have to have a and b together. But does it matter if I do a first or b first? Not really. I can do a or b first. It doesn't matter. But they have to happen before I can do the plus. Okay, ducks? So before we get to that, though, I would like to show you something something else. Okay, so in homework 12, we talked about trees, inductively defined trees. Sorry, exercise 12.1, and we talked about in-order traversal, right? You have a tree and you want to turn that tree into a list, right? And we said, oh, okay, walk all the way to the left and then pick pieces up as you walk along, right? A generalization of in-order traversal for trees is known as depth-first search. Okay. So here is a graph. Oh, sorry about that. So here is a graph, right? And we want to walk along the graph. We're going to start at E, and we're going to walk along the graph, trying to find everyone else. Okay, so imagine you live at E, and you're going to try to find all your neighbors. Okay, well, you're at E. You can go to your neighbor F, or you can go to your neighbor G. All right, let's go to our neighbor F. All right. Now that we're at our neighbor F, okay, well, where can we go from here? We can go either down to C or down to D. All right, so let's pick one of those. All right. So we decide to go down, we're going to pick one of those. Which one shall we pick? Let's go down to C. Okay. When we go down to C, then we realize we can go down to A. From A, we can go back up to B. And that's all the places we can go. But unfortunately, we haven't walked down to G, right? So so the way we're searching is we picked some place, we walked along, and then we realized, wait a minute, there's some other place we have not yet visited. So let's go start there and see where else we can go, right? So this works in general for arbitrary DAGs. It doesn't work just for trees. Trees was in-order traversal. This one will work everywhere. Okay. So are there any questions about this? Okay. Before we move on? There you go. Good. All right. So the interesting thing here to note is that we're coloring things before we visit, right? We're starting at the very top, and we're like, all right, I'm here at E, and I'm gonna walk. Okay. As we walk, we're gonna mark everything we see with red. Now we saw F, we mark everything with red. All right. So everything we visit, we mark it with red. Yeah, Jay, happy to do so. So the idea is we're in this graph, and we want to walk everywhere. Okay, so we're starting at E, and we're saying, can we get everywhere? Well, I'm at E. I can see F and G. So let me mark red all the places I actually visit. So I visit F. So let me mark that red. Now I'm at F. I go down to B. Notice I'm going deeper and deeper. I go as deep as I can first. So I'm at E. I go down to F. Now I'm at F. I go down to B. Right? Notice F and G are siblings with E as the common parent. Right? So from E, I can visit F and I can visit G. But I decided, let me visit F, and then let me visit everywhere possible via F. And then I'll come back to G. Okay? So I'm at E, I went to F. From F, I went to B. Now that I'm at B, I can go to C or to D. Let me go to D. I've gone to D, great. Now at D, I can go down to C, or I can go down to A. Okay, let me go down to A. Now that I'm at A, the only place I can go is to B. But wait, B is red. I was already at B. I already visited B. We had tea and crumpets. It was delicious. I already visited B. So let me go back, right? Let me go back to A. Is there anywhere else I can go? Nope, no other place to go. Okay, let me go back to C, to D. Now that I'm back at D, where else can I go? Oh, I can go to C. Okay, let's go to C, all right? So now I'm at C. Where can I go in C? The only place I can go is down to A. But I already visited A. We hung out, we played video games. All right, let me go back. Is there anywhere else I can go? Nope. All right, let me go back to my parent. How did I get to C? I got to C from D. So let me go back to D. Hey, D, is there anywhere else I can go? Nope. Okay, let's go back from D to B. Hey, B, is there anywhere else I can go? Nope, we visited everybody. Let's go back up to F. We're at F. Hey, F, is there anywhere else we can go? Nope. Okay, let's go back to our grandparent of all, E. So E is where we started. We went all the way down to F and visited as much as possible via F. And now we're going to go to G. Okay, now I go to G, and then from G I visit to D and F, and I've already visited those. So I go back and I'm done. No more visitations. It's exactly recursion. Here's the algorithm if you are so interested. The algorithm is super, super simple, right? For every neighbor that I have not yet visited, if that neighbor is not visited, then please go visit that neighbor and all of its kids. So that's the algorithm right there. Three lines. Really, really simple. Okay. And we said, hey, let's do some pre-processing before the algorithm runs. The pre-processing we're going to do is we're going to color some stuff red. Okay, and make some files. Okay, so to make all these diagrams, I colored them red, but the main algorithm is right here, just this little part, right? The current node we're at is visited. Please set that data to be visited, set it to be true. Then look at all the neighbors. If those neighbors are not visited, please visit them recursively. Okay, so very, very simple. Okay, now here's an interesting thing. We set the data before we do the visit. Let's change it up. Let's change it up and see what happens. Yes, in the next slide, I'll get to the topological sort from the book as well. So let's change this to be post and see what happens when we do it this way. Okay. So we haven't gone to topological sort yet. I just want to show you this. So notice now, because we're doing the coloring after we visit, all right, the first thing that happens is we color the very last step we take. So here, we colored the very last step. Then here, we're covering the step before the last step. Then the one before, then the one before, all the way till we color it. So it got mirrored, okay? So I just wanted to show you the effect of doing that the other way around. And now, let's look at something slightly more fun. Where is shuffle? Sorry. Control S. So let's shuffle some of these diagrams around. when we shuffle the things around, so this is what I was talking about earlier about it being topological. You can move them around as long as the edges stay where they are. So notice here, this is the same graph. It's the exact same graph, same graph, same graph. But notice it looks a little bit different, right? It looks a little bit different. And where do we start this time? This time, instead of starting at E, we started at D. And we're doing the same thing. Hey, D, where can I go? We can go to A, or we can go to C. OK, let's go to A. From A, we can go to B or C, and then we just continue, right? And then we just keep going until we visit all of them. OK, so it's the same recipe, but the idea is because you can move the nodes around, it looks like a different graph, but it is the same one. And that's why what we're going to get to next being topological sort. OK, so the cool thing about topological sort is it gives us a nice way to organize a graph into a sequence. Do this first, then this, then that, then the third one. So here's an example. Keyword argument, not one of pre. Sorry, this one. Let's say this is post. We're going to do this at the end. OK. So here's a simple graph. You're taking some classes at the school. OK. And to take class 5, in the 5th year class, you have to take classes C3 and C4. C3 depends on C1 and C2, and C4 depends on C2. So you have to take these classes at your university. How should you take them? OK, well, one of the first things is you can take C1, then you can take C2, then you can decide to take C4, right? Because if you took C1 and C2, you can take C4. You have the prerequisite to take C4. Then you can take C3 because you took C1 and C2, which meets the prerequisites, and you can take C3. And then finally, you can take C5 because you took 3 and 4. OK, so that's one way you could take these classes. Let's try another way. So here's another way you could take these classes. You could start off, last time we started with C1, you could instead start off with C2, right? Why are we allowed to pick different ones? Because they're not comparable. Just like up here, we had 2 that were not comparable. It doesn't matter which one you do first. You can do C1 first or C2. You can take either classes. You can take them in the same semester. OK. After you take C2, we'll say you can take C4 because now you met the prerequisite. Then we take C1, and so that way we can take C3, and then we can take C5. Right. So this graphical structure can be arranged as a sequence or as a sequence, right? And notice it's the exact same algorithm as before. You just recursively keep going, right? You just recursively keep going. We're calling the same depth first search, but now we're just keeping track of things at the end instead of at the beginning. Okay, next. So hopefully that was a little bit of some fun stuff. And the slides have already been posted to Avenue, so I won't spend too long on them. But again, instruction scheduling for 2GA3 next term. OK, I showed you just 2 right here, right? But here's a bunch more for this particular graph, right? Somebody's asking, isn't C2 a prerequisite for C3? Yes. So you have to take C2 before you can take C3. So right here, I took C2, and then later I did C3. And right here, I did C2, and then later I did C3. Right. So whenever I did C3, it was after I took C2. So I hope that helps. Right. OK. So I've shown you the algorithm here in Lisp a little bit. I'll post these notes online. But the heart of the algorithm for topological sort is in fact this depth first, right? Which you essentially already saw in homework in exercise 12 for in-order traversal of trees, right? So the idea is just go down as much as I can. When I can't go down anymore, or I've already seen things, go back up. Okay. And of course, we need it to be acyclic. Otherwise, we're going to end up going in circles. So we're keeping track of these things. All right. We look at them if they're red. Then we know that we've already gone there, and we won't loop. All right. So for example, here's D, C. All right. Go back to A, go to B, go to D. That's a circle. It's a cycle, and we keep track of it by marking things red. Okay. In graph theory, to mark things to know where you are. Okay, ducks. So hopefully you've enjoyed this graph theory stuff. I'll post the code online as well in case you're interested. The book does have the nice pseudocode. It's just essentially the same thing. Start off with all the nodes you have, all the vertices. Your sequence is essentially empty at the beginning, right? And what you do is you say, hey, while I have more nodes to visit, right? While they're not all red, while there's more nodes to visit, let me pick one, right, that I'm touching. Let me pick an adjacent one. So here we just said, look at the ones that you're touching, right? So pick one that's adjacent, right, or induced by the subgraph, okay? Now that I picked it, put that one in my sequence, and then color it. So now it's not black anymore. So VS is all the black ones, and we get rid of them by making them red each time, okay? So this algorithm is the same thing right here, okay? This is expressed as a while loop. Over here, we just expressed it as a recursion. That's all, okay? Of course, it could be made more efficient. So by expressing it here as recursively, I've made it quite efficient for you. I've put a little tiny analysis in case you're interested. But if you try to work just with loops, then you have to keep track of the stacks and queues, all right, for what you have visited and what you haven't, and what you have to keep track of. So keywords to remember going forward, like in the algorithms class you'll take next year, is a cons list stack, and a SNOC list is called a queue. Okay, so because you're familiar with both kind of lists, going forward, you already know two additional data structures. Cons lists are stacks, SNOC lists are queues. You've seen trees. Hopefully we'll get you some exercises on binary search trees, and you've seen graphs, the granddaddy of them all. Okay, ducks. So I'll leave this topological slides here for you, for the interested, right? What's important for me is for you to see why they work, to get the idea. The optimization is neat, and I'll leave that to the interested students, and it's also in the book. So I won't dwell on the optimization, but I think it's important for you to see it nonetheless. So it will stay in the slides. Okay. One cool thing is we've come essentially full circle, right? So not too long ago we were talking about these commands, right? Command correctness. We were saying if you have a programming language with these features, you can do these things. And now we're saying, and now that we have access to relations, we can model the actual syntax of our command language as if it was a mathematical relation, right? So I just want to mention that quickly. In third year classes, you will do a lot of this kind of stuff for semantics, where you'll say, hey, I have some of these, I have some sentences, I have some words, I have some phrases. What do they mean as relations? What do they mean as graphs? What do they mean as functions? Okay, and sometimes it's easier to work with things if they have a functional interpretation versus having a relational interpretation. Okay, so for example, we can take a command and we can think of it as a relation between states, right? Remember, a state is an assignment of values to variables, right? So we can say every command is really a relation between states, and that's how we think about it, right? So an assignment command, we think of it as taking a state S to the new state, right? That maps X to the evaluation of E under S, Okay, so X becomes E means whatever state your computer was in before, whatever state your computer was in before, all right? Let's look up, so this is relation override. We're gonna look up using the previous state, all the variables, and then use those to evaluate the expression E, okay? And then likewise for if, right? We make a union now, right? And we make use of domain restriction and anti-restriction. And while is this reflexive transitive closure. We might run or we might not. So just some things I think useful for you to know since we have the language to talk about them now. So you'll see semantics definitely in upper years, possibly next term as well. Okay. So just trying to wrap up some stuff that you'll see. Not everything easy to test you on, but just to show you some stuff. So we've talked about this hashtag before. It means count the number of elements, right? So when you count the number of elements and you divide by all possibilities, that's called the probability, right? It's the likelihood or the chance of doing something. And we can talk about it now because we have the appropriate set theory and quantifier theory, right? So one of the things we require for a probability distribution is to say, hey, every value I'm thinking about should have a likelihood between 0 and 100%, and the probability assigned to each thing I'm talking about should be between 0 and 100. So when I add them all up, I should be distributing 100% over my entire state space. Okay. So nothing too exciting, nothing too interesting. That's why it's only 2 slides. Probability theory has atrocious notation. So, but we'll try to get maybe a tiny exercise out. I'll try to get one out maybe today. There's probability theory is really just hiding inside sigma, right? Discrete probability theory is just hiding inside sigma. There's nothing new there, but I think it's important for you to actually see it and just be exposed to it. Okay. Just as set theory has subsets, probability theory has events, right? Which is just another way to say subset. Okay. So I'm just going some of this stuff quickly, trying to show it to you, and this is really where I wanted to end. So I'm glad we made it. So going full circle again, so this is really exciting. We started the term with these inference rules, and we said, hey, you know, there's a substitution inference and some others. So here is, if you recall, all the way back, all the way up here, right? We had these inference rules, right? Oh, right. You can, when you were little, you said 12. And then you said 7, and you said the rule I'm using is called addition, and then the result is going to be 17. And then earlier in this class, chapters 1 and 2, we said, hey, if you have some premises and you have some rule R, you can get some conclusion C. So for example, modus ponens, function application is one of the rules we've had implicitly being used. And we mentioned that these are really just trees, right? It's all just trees, and when you make a rule, that's a constructor for a tree. Okay, so that's I think that's pretty neat. So maybe we can do one more example before I run out of time. So let's do. So you'll see this kind of natural deduction presentation almost very likely next term. Okay, so it's important to see these and be familiar with them. But let's do a data type. Let's call it n, and n has home. Nope. Stop, or it has an arrow followed by an n. Okay. So it has a stop sign or an arrow followed by an n. What's the induction rule here, right? So who wants to guess? Okay, well, it could be P with X could be the stop sign, right? Right, that's one option. Another option for X is it could be an arrow going to some other one. So for all X of type N, I could have P is already true, and now I need to show P with X being replaced by arrow goes to X. Okay? Yeah, exactly. All right. So let me do one more really quickly because we clearly have the time. Let's do T. T is stop sign, or here's the cool thing. It could be another T, an arrow, a number, and then another T. What's the induction rule for this one? It's almost the same induction rule as above. So the induction rule is going to be, for T, is going to be either stop sign, or I can consider a left child, a right child, all right? And I can consider an actual natural number and say, suppose it's true with X being the left child, and it's true with X being the right child, then it will be true with the left child and goes to the right child. Okay, so this is another example of this structural induction. And of course, this is just trees again, right? Fancy T because this is trees, fancy N because it's natural numbers. I just use different symbols to show it to you, right? I have 2 branches, I have 1 branch. Anyhow, we've run out of time, so I won't keep you any further. I hope you're enjoying, you're learning, you're excited for the term to be over and for the holidays to occur. So I hope everyone has a fantastic Friday and a great weekend. And I will be here to answer questions.